Good afternoon, dear students. Here today we are going to discuss about estimation of dissolved oxygen present in water by Winkler's azide method. This method is a titration method, iodometric titration method, which was first designed by Winkler. So the name Winkler's azide method. Now, what is dissolved oxygen? It is the amount of oxygen, gaseous oxygen present or dissolved in water. Now, dissolved oxygen is the most important indicator of health of a water body and its capacity to support, its ability to support a balanced aquatic ecosystem of plant. Higher dissolved oxygen level in water indicates better water quality. If dissolved oxygen levels are too low, some fish or aquatic life may not be able to survive. Okay? A lower oxygen level indicates that more amount of microbes are present, or more of organic matter is being dumped into the water body. How can we measure the amount of dissolved oxygen present in water? Either by titrometric estimation using iodometric principle, or by colorimetric method, or by using some electrodes or sensors. Today here we are going to discuss estimation of dissolved oxygen by titration method, that too Winkler azide method. In this method, what are the different chemicals that are required is MnSO4, then alkali iodide azide solution, simply called as alkali azide, concentrated sulfuric acid, starch and sodium thiosulfate are the chemicals that are required. Now, see, first we'll discuss the procedure, how to perform it, and then we will switch over to the principle. So the first thing what we need to take is, this is a BOD bottle. It is of 300 ml capacity having glass stopper. So you take a 300 ml BOD bottle with a glass stopper. The bottle should be clean. Fill the bottle completely with water, and then stopper the bottle and invert the bottle to remove excess of water. While you are filling the bottle with water, take care that there is no dissolution of atmospheric oxygen into it. You should avoid bubbling during filling of the bottle. Once the bottle is filled completely with water, stopper the bottle and remove excess of water, and then with the help of a pipette add 2 ml of MnSO4 solution into the bottle. Okay, you have to take care that the tip of the pipette should be inserted inside water. The tip of the pipette should not be outside, it should be immersed inside water, and then you release the 2 ml of MnSO4 solution. Followed by that, you have to add 2 ml of alkali iodide azide solution. You have to add alkali iodide azide solution. When you add alkali iodide azide solution, brown precipitate is formed. Brown precipitate is formed. Allow the brown precipitate, you can see this, allow the brown precipitate to settle down. Once the brown precipitate settles down, you have to add 2 ml of concentrated sulfuric acid. What do? We add 2 ml of concentrated sulfuric acid. Mix well. Every time, whatever solution you add to the bottle, you have to take care that the tip of the pipette should be immersed inside the bottle, inside the water present in the bottle. Okay, you add 2 ml sulfuric acid solution. When you add 2 ml of sulfuric acid solution and shake the bottle, the precipitate will dissolve completely. The precipitate will dissolve completely. Now, from the bottle, collect 203 ml of water sample. Right? From the bottle, you have to collect 203 ml. It will be golden yellow in color. The color will become golden yellow. The precipitate will dissolve and it will almost be golden yellow color in the bottle. Now, take out 203 ml of solution of water from the bottle and put it into a conical flask. The conical flask already contains 1 gram Ki. Right? What you have to add? 1 gram Ki into the bottle. No need to add potassium iodide, it is already there in the alkali iodide azide solution. You just take out 203 ml in the bottle, and then you have to little bit you can say dilute the color. The color is very dark yellow, so you just dilute the color by titrating it with 0.025 normal of sodium thiosulfate solution. Sodium thiosulfate solution is taken in the burette, little bit of, make the color little bit lighter, and then like you add 1 to 2 ml of sodium thiosulfate solution from the burette, and then you have to titrate the amount of iodine liberated by using starch as indicator. So in the conical flask, add say 2 to 3 drops of starch indicator. When you add 2 to 3 drops of starch indicator, the color will change to deep blue. The color will change to deep blue. Now, with the same burette, from where you have added 1 to 2 ml of thiosulfate into the conical flask, with the same burette, titrate the solution in the conical flask, which is blue in color, till the blue color disappears, or the blue color becomes, you can say blue color disappears, or till the change in color is from blue to white or blue to colorless. Okay, so what you have to do, take a BOD bottle, fill it completely with water sample, stopper the bottle, remove the excess of water. Into the bottle add 2 ml MnSO4 followed by 2 ml alkali azide solution. Okay, when brown precipitate appears, shake well, allow the PPT to settle down, and then add 2 ml concentrated sulfuric acid. When the precipitate will dissolve, the color will be almost golden yellow. Take out 203 ml of this solution into a conical flask. Make the color little bit lighter by adding 1 to 2 ml of sodium thiosulfate solution from the burette. Then add starch indicator, blue color will appear. Titrate, continue titration with sodium thiosulfate solution till the color changes to white, or solution becomes colorless. Now what happens here? Potassium oxide is oxidized to iodine. See, alkali iodide azide solution is added into the bottle. It is oxidized to iodine with the dissolved oxygen present in the water sample after adding MnSO4 and NaOH plus Ki, that forms alkali azide solution. Okay, so what happens when MnSO4 and alkali azide solution are added to water? Whatever dissolved oxygen is present in water will liberate the iodine equivalent to the amount of dissolved oxygen present in water, and this iodine which is liberated is titrated with sodium thiosulfate using starch as indicator. Amount of iodine liberated is equivalent to the amount of dissolved oxygen present in water. What happens? The basic manganic oxide formed from NaOH and MnSO4 act as oxygen carrier to enable the dissolved oxygen in the molecular form to take part in the reaction. What happens? The dissolved oxygen present in the sample oxidizes Mn plus 2. MnSO4 we add, no, there the valency of MnSO4 manganese is Mn plus 2. Mn plus 2 is shifted to higher valency by dissolved oxygen. So dissolved oxygen oxidizes MnSO4 to its higher valency, okay, right, which gets precipitated as brown hydrated oxide after addition of alkali azide, that means NaOH and Ki. Okay, so MnSO4 which is added is oxidized by dissolved oxygen, and it is changed from Mn plus 2 to its higher valency, where it forms a brown hydrated oxide. Okay, so a brown precipitate of manganic oxide is formed. Upon acidification, when you add H2SO4, the manganese reverts back to its divalent state. Mn plus 2 is reverted back, and equivalent amount of iodine is liberated from the Ki present in alkali iodide azide solution. Okay, so first Mn plus 2 is oxidized to higher valency, where it forms a brown hydrated oxide. Upon acidification, it reverts back to its original state. When it reverts back to its original state, equivalent amount of iodine is liberated from Ki. The liberated iodine is equal to the amount of dissolved oxygen. It is titrated against sodium thiosulfate using starch as indicator. Okay, so again, DO present in the sample oxidizes equivalent amount of divalent manganese ions to higher valency states and forms brown hydrated oxide. Rest of the manganese ions from divalent hydroxide precipitate. Upon acidification with sulfuric acid, the higher valency manganese ions are reduced to divalent ions. Okay, and iodine equivalent to the dissolved oxygen content in the sample is liberated. This liberated iodine is to be titrated or measured with standard sodium thiosulfate solution and starch as indicator. So what is the procedure? So these are the reactions which take place when you are performing the titration. Okay, when you are performing the basic reactions. Right. So procedure you know now. You have to take 300 ml of water sample in the bottle, fill the bottle completely, stop of the bottle, revert so that excess of water flows out. Then add 2 ml MnSO4 followed by 2 ml alkali iodide azide. Okay, precipitate will appear, shake well, allow the PPT to settle down, add 2 ml H2SO4 so that the PPT dissolves, take out 203 ml from the bottle into a conical flask, lighten the color by adding sodium thiosulfate from the burette, add starch indicator, the color turns blue, titrate till it becomes colorless. Okay, and note the volume of thiosulfate required to convert blue color solution into colorless, and calculate the amount of dissolved oxygen. It is actually the amount of dissolved oxygen is equal to the amount of thiosulfate required. So amount of dissolved oxygen present in water sample in milligram per liter is equal to A into N into 8 into 1000. A multiplied by N multiplied by 8 multiplied by 1000 divided by volume of sample taken in the conical flask. We have to take it 200 ml because 203 ml we have taken out actually, but it is equivalent to 200 ml because this much amount of 3 ml of sample is lost when we are adding the MnSO4 or H2SO4 or alkali azide into the bottle. So you have to take 203 ml in the conical flask, but it is equivalent to 200 ml only. Okay, so A is the volume of thiosulfate required multiplied by N, that is the normality of sodium thiosulfate, 0.025 multiplied by 8, that is the equivalent weight of oxygen, multiplied by 1000 because we are calculating it for 1 liter, and divided by volume of sample, that is 200 ml. The amount of DO will be equivalent to the amount of thiosulfate required. This is how we determine the amount of dissolved oxygen present in water by Winkler azide method or by titration method.